Greetings and welcome back for another Music Theory Bite. In this video, I'm going to be talking about the physical properties of sound. Why? Because music is, at least in part, made up of sound. So understanding how sound works is pretty important for understanding how it can be used in music. So if that sounds like something you'd like to learn more about, then this is the video for you. Let's begin by talking about sound. What is sound? Well, sound, quite simply, is waves of energy that travel through a medium from the source that creates the vibration that causes the energy to our ears. And our ears pick that up and turn that into something that our brains can understand. That energy, as it moves through the air, consists of the air molecules compressing against each other and then expanding back. Sound needs some sort of medium, such as air, to travel through. So, when you're watching that science fiction movie and you see the spaceship blow up and it makes that nice loud bang, well, that's not exactly accurate because there's no medium for the sound to transfer from the cause of the vibration, the exploding spaceship, to your ears. In space, any sound that you have, well, you wouldn't hear it because it can't be transferred. Likewise, if you spend any time underwater, you'll notice that you hear things, in some ways, much more efficiently than you do when you're outside of water. That's because water is a very efficient medium for transferring vibrations from their source to your ears. But since humans spend most of their time outside of water, we're mostly concerned with how sound gets transferred from the cause of the vibration, the cause of the energy waves, to our ears. We can chart these vibrations, these energy waves, using a tool called an oscilloscope. It gives us a visual image of the sound that we are hearing by drawing a chart of the energy waves. Let's look at one. I'm going to use a program called Audacity. It's a free program that can be used to create and manipulate sounds. It's a wonderful program for audio production. And we're going to do some very basic sound construction. But first, we need to figure out what we're seeing. A very simple sound, a sine wave, looks like this. We can think of this chart as being kind of like a graph in a math class. That is, we have an x-axis, which runs horizontally, and a y-axis, which runs vertically. You'll see along the top some numbers there which indicate time. And so our x-axis is going to be our representation of time. You'll notice that the numbers are very small and they increase in very low amounts, very small amounts. That's because sound moves very quickly. In order to see the actual sound wave, the shape of it, we need to really dig really deeply into the sound in order to make sure that we're seeing what it looks like. On the y-axis, you're going to see some other numbers there. And this is a measurement of strength. And those are measured usually in what we call bells or decibels, which is a tenth of a bell. And that's just a measurement of sound energy. Let's take a look at the x-axis again. What this tells us is what we call wavelength, that is, the length of each of the waves. And if I mark one waveform here, you'll notice that that shape repeats over and over and over again on a standard sine wave type of sound. How frequently those waves repeat is what tells us the frequency or pitch of the tone that we are hearing. For example, some standard tones are, you may have heard the term A440. That's the A above middle C, which vibrates 440 times per second, or the unit for that is called hertz, 440 hertz. Middle C is approximately 261.6 hertz. That is, we hear a vibration 261.6 times per second. The higher the number, the faster the vibration, and the higher the pitch. Frequencies at specific multiples of pitches create the same pitch, the same letter name, at octave intervals. So, for example, if we double middle C, 261.6 doubled equals 523.2. We will end up with the C above middle C. If we have that number, take 261.6, cut it in half, we're going to end up with 130.8 hertz. And that is the C below middle C. Let's talk again about the wave height. Sometimes we'll call this amplitude. This tells us how loud the sound is. If you take a look at the axis line, the x-axis, it's marked 0. That means no sound at all. the air molecules aren't moving at all. The lines above and below that zero show the compression and expansion of the air molecules, show you the amount of energy that goes into it. In general, the higher the line above or below the x-axis, the louder the sound. Finally, we have waveform, or the shape of the wave. The shape of the wave determines the specific sound, called timbre, that we hear. Two instruments playing the same note will share the same wavelength, but the waveform will differ. The shape of the wave will differ, creating a unique sound. Here's what it looks like, the sound of a piano playing middle C. And right next to that, I recorded my voice singing the same pitch, middle C. Notice how the repeating part of it, which I've highlighted here with the red lines, is identical in length. But the shape of the repeating part is different between the piano and my voice, because even though we're singing the same note, producing the same note, it sounds different on a piano than it does when I sing it. Waveforms or timbres are generally created by adding different tones together. That is, when a tone is created by vibration, it bounces against things and bounces back, and that bouncing back creates other tones in the sound. Most sounds are a blending of multiple pitches in different amplitudes or loudnesses. So we can think of creating a sound as being a sort of recipe. Take this pitch at this level, add in these other pitches at these levels, and you're going to end up with the particular sound of a piano or trombone or my voice. These other sounds are called harmonics or overtones, and the relative strengths of these is what creates the different waveforms. The energies of the different pitches are added together to create the new waveform. Let's see how this might work. First, let's take a regular sine wave that looks like this. If we add a second sine wave an octave higher, notice how the waveform is the same shape, but now we fit two of the faster waveforms into the same space taken by the slower waveform. Creates a 2-to-1 ratio, which creates an octave. If we add those two things together, that is, all the plus energies above the line are added together, and all the negative energies below the line are added together. And if you have plus in one place and minus in another place, you'd be subtracting the energies below the line from the energies above the line. When we add those two lines together, the waveforms can end up being quite complex. Notice how this one creates a newly shaped waveform. This new waveform, or timbre, is the addition of these multiple pitches and amplitudes, creating a unique waveform. If we change the shape of the waveform, we will change the timbre of the sound. For example, when you hear a musician complain about distortion, what is happening is that the sound is being played at a volume or amplitude that the equipment that is being played through can't handle, because all equipment has limited range. So if I draw red lines on my chart here, anything above the red line, if this is the limit of what my equipment can handle, or below the bottom red line, will be cut out, meaning that the top of the waveform and the bottom of the waveform is going to be squared off, creating a different sound. That's what distortion is. The extremes of the waveform are chopped off, changing the quality's timbre because the shape of the waveform changes. When we're talking about these harmonics or overtones, the specific notes that go into a sound are usually fairly regular. This is what musicians call the Overtone Series. We have what we call the fundamental or first harmonic, and this is an octave higher than the fundamental note. Next is a note a perfect fifth higher, or a perfect 12th above the fundamental, creating a second overtone or third harmonic, and so on. The Overtone Series continues on well beyond the scope of human hearing, and most musicians memorize it up through the 16th harmonic. On this chart, you'll see the harmonic number written above each pitch, and the frequency in hertz of each of those pitches approximately below the pitch. Some of the pitches are using filled-in note heads, and those are tones that are out of tune from what we normally have in our musical system. But notice all the Unfilled in note heads are notes that we typically have in our musical system. You might notice that you can also use math to figure out the frequencies of the overtone pitches by using the numbers of the harmonic series. For example, our third harmonic is a perfect fifth above the second harmonic. In this case, the G is at 392.4 Hertz, while the C below it is 261.6 Hertz. The ratio between those two numbers is approximately 3 to 2, and notice that matches up with the harmonic numbers. The G is harmonic number 3, and the C is harmonic number 2. I'll talk more about the harmonic series and all the math that goes into it in another video, but for now it's enough just to know that the harmonic series exists, and every sound consists of some combinations of these tones in the fundamental tone that you hear. Getting back to our oscilloscope chart, there's one more concept we need to look at, and that's called sound envelope. The envelope is the shape of the overall sound and consists of several parts. First, we have an attack. Next, we have a sustain. And third, we have a decay. And if we zoom in on the visualized sound, we'll see that the height on this chart still represents the loudness or amplitude. The waveforms are really squished together on this one. You'll notice the scale at the top is much longer than it was in my other oscilloscope charts. And so if we were to zoom in on this, we would see all those squiggly waveforms all over the place. That still represents pitch. And since this is a visual representation of a non-musical sound, a sound of me talking, then we're not going to see a regular pitch because we use all sorts of different pitches when we talk. And finally, we see the decay, which takes us out to the end. So with this information, we should be able to decipher a little bit about how sound works and the different properties that go into creating a sound. Well, that does it for this video. If you found it helpful, as always, make sure you like it. Feel free to leave constructive comments below, and make sure you subscribe to my channel for the latest music theory bites as they become available. Until next time.